This presentation is divided into 3 parts. The first part is basically a general introduction to satellites and how to use them. The second part that I want to spend a little time on, particularly as I was talking with Phil, since he'll be working with the SEM coordinator at your local school, is a program called ARIS, Amateur Radio on the International Space Station. This is a program that we'll go into the details. Suffice it to say, it allows the students to talk to an astronaut on the ISS real time during a 10-minute pass and ask them questions. It's a lot of fun for the radio club. I will tell you that the start is really intense because you've got 300 eyes staring at you and you're saying NA1SS, K4SQC, and all you hear is static. It's kind of like, oh my gosh, is this really going to work? But it is a wonderful program. The third part of the program talks about things that AMSAT has in the future, and we can spend more or less time on that depending how the rest of the night goes. How many of you are currently or have in the past operated satellites? AO40 vintage satellite, or yeah. So most of you are new. I invite questions as we go because I really would like you to leave tonight feeling comfortable with the idea that particularly with the FM satellites, you can work them. You can certainly hear them if that's what you want to do. So with that, let's get started. It is a great time to work satellites. There's a great working base in orbit. For this presentation, I prepared a list of potential orbits, and I had 20 satellites on the list. 5 years ago, if I would have given you this, there would have been 3 or maybe 4 satellites on the list. So it really is a good time. There are more launches every week. They are mostly of CubeSats, something we'll talk about as we get going forward. I listed some URLs here, and don't try and copy them down. I'll give you a copy of the presentation on a thumb drive so you can stick it on your website and you can just get them from there. Suffice it to say, you really need to keep track of things. There's another launch going up the end of this month that will have 56 CubeSats on it, 2 of which, one is from Georgia Tech and the other is an AMSAT list, so there are more and more all the time. Some of these launches occur when a satellite is carried to the ISS as part of a resupply mission. And then the astronauts, it's really great to see the videos. They literally throw them out of the ISS. Now, when they throw them out of the ISS, they last about 2 to 6 months before they come out of orbit. But nonetheless, they are up there. There we go. This is a page, www.amsat.org status. It's a bit of an eye chart, but it gives you a current listing of every operational amateur satellite that's up there. And it's useful for a couple reasons. It just lets you kind of know what's going on. These that are in yellow means that the telemetry or the beacon was heard. These that are in red means somebody listened but they didn't hear anything. Blue means the transponder was on and people were making contacts through it. So these are all the satellites down the side, the dates, and whether or not they were heard. A very useful page just to help you figure out what's going on there. One of the things that I think is unfortunate still about the state of the art with satellites is the satellite makers like to list every satellite that was ever up there, whether it's functional or not. And that makes it kind of difficult to know, well, which ones can I really talk to? This is a great page to do that. The point of this page, and this is only half the page, is the number of satellites that are up there right now that you can, as a radio amateur, you can work with. This, working the satellites, this is a picture of a CubeSat. This, slightly beat up because it's been through hundreds of hands, is a one-to-one model of a CubeSat. By international standard, it's 10 centimeters by 10 centimeters by 10 centimeters. It weighs 1.3 kilograms. And so when you're talking to AO91 or AO92 or AO85, many of the current satellites, this is what you're talking through. These are solar cells on every panel. There are 7 boards in here. One board is the internal housekeeping unit, the computer that runs it. 2 boards are experiments, and we'll talk about that a little bit later. There are 2 radio transponder boards. The middle board is always the battery board. The batteries we are currently using are still plain old NiCad C cells. It's amazing if you unwrap a C cell and take all of the consumer packaging off the outside of it, how small they really are on the inside. Somebody usually asks me, why don't we get with it and use lithium batteries? And the simple answer is because we know the characteristics of NiCads in space, and they don't explode or catch fire, which would be a bad thing. So I'll go ahead and pass that around. That's a picture of actually one of the current ones. I can't remember if it's AO91 or AO92, ready to be launched. The white thing on the side is a ready to launch pin that before they launch it, they'll actually pull it out. I don't know if you can see, but can you see the piano wire that's kind of wrapped around these pegs? Based upon its length, that's the 2-meter quarter wavelength. The end is held to a resistor with some fishing line. When it gets into the proper place in space, a command is issued. A little bit of juice is sent to the resistor, that's the peg. It heats up, it melts the nylon fishing line, the antenna springs out, and now we have a quarter wavelength on 2 and a quarter wavelength on 440 coming out the other end of the satellite. So, what are the ways you can work a satellite? The first and easiest one is just listen to them. Particularly, they're all either 2 meters up or 2 meters up, 440 down. The current ones are almost all 440 up and 2 meters down. Some people have asked why it's that way. It's easier to generate RF at 2 meters than it is at 440, 435 actually. In a satellite, the entire issue is the power budget. And so they said, well, let's let the ground station that basically has infinite power compared to a satellite, we'll let them generate the 440 RF, and we'll let the satellite generate the 2 meter RF. The other advantage to us, anybody think what might be the problem if you're working 2 meters up and 432 down, and you got a big preamp sitting on the 432 side? You have trouble desensing yourself. 432 is the third harmonic of 2 meters. And so there are all kinds of elaborate filters. In the old days, we used to talk about a mode J filter to try and filter out that 2 meter juice before you got onto it. Telemetry monitoring and reporting, I'll talk a little bit about that. All of these satellites, AO85, AO91, AO92, all have experiments in them. 85, 91, and 92 all have an experiment from Vanderbilt University. They wanted to know how typical semiconductors behave in the radiation of space. And so their 2 experiment boards have those semiconductors on them, and they keep track of how many times they restart. That information is sent back. It's called DUV, data under voice. It's kind of a slick trick. What they did on the satellite was they took the part of the spectrum where normally in 2 meter use you'd put the digital PL tones, and they actually encode the data in the PL tones. You can monitor that data, collect it. It goes to Vanderbilt University. They use the data in their research. When the first group of amount of data came down, one of the AMSAT guys was talking to the primary investigator from the university, And he told them that the data had not confirmed his hypothesis at all. And so the amateur radio guy thought, oh, this is horrible. The experiment must have failed. And of course, the professor said, oh, no, no, no. This is wonderful news. Now I can write a grant, and I can get more money to figure out why my original hypothesis was wrong. The next most complicated way to work satellites is with the FM transponders. This is where most people start. It's certainly where I started. And it's really like a crossband repeater in the sky. It's either 2 meters up and 432 down, or the other way around. It is single channel, so big dog wins, which can be a problem. If any of you have an aspiration of making a satellite contact on field day, my suggestion is have someone who can work CW or sideband do it on one of those satellites, because on field day, the FM satellites are an absolute zoo. I actually, 2 years ago, did make an FM contact that was loggable. It took 3 passes of the same site with the same station to get enough information to have it be a valid exchange, because somebody was always stepping on me when I was trying to do it. The most complicated, but one of the funnest ways to work the satellite, I think, are the linear transponders. As opposed to being a single channel, a linear transponder takes a piece of spectrum, 20 kilohertz to 100 kilohertz, and you can put a number of CW or sideband signals in there. So there are multiple conversations going on at the same time. The most recent addition to that is the XW series. This was a series of 6 Chinese satellites that are up there, and they're a lot of fun to work. Here's an example of the telemetry. It's another way to work it. I've already explained transponder plus data satellites. This is kind of a good deal for us. You might want to ask why we get involved with the universities. In the olden days, AO40, which is one we just mentioned, was a satellite that was in a very high elliptical orbit. And it made it really fun to work, because when it was out there a few thousand kilometers, it's almost like it sat still in the sky. So you could just point at it. This was launched in the 80s out of Guyana on an Ariane. When, if you think of those days, most of the rockets blew up most of the time. And so the commercial people weren't too interested in putting their satellites on rockets that were unproven. That's where the amateur community came in and said, well, we'll give it a try. That satellite was a wonderful satellite to work. There is a spare space frame for it that sits in Germany. The cheapest launch we can find for it is $10 million. There aren't too many ham communities that have $10 million sitting around looking for someplace to spend it. So we partner with the universities. We build the airframe, the space frame, and the radios, the avionics. They put in the experiments. And NASA, under the Alana program, gives us launches that are essentially free. So it's a great way to get more satellites in space without having to spend lots and lots of money for it. If you're interested, there are a whole host of data-only satellites. I won't talk too much about them. Some people spend their whole time simply decoding them. What does a telemetry operation look like? I had an old computer at home, and so I put an SDR radio on it. This is in the corner up here, the far right-hand corner is SDR sharp that's tuned to the satellite frequencies. Below it is a program called SAT-PC32, which keeps track of where the satellites are and automatically switches the frequency to the next satellite. This is something called FoxTerm, which is the software that actually decodes the data. I have this running all the time in my basement. The antenna is simple. It's a quarter wavelength ground plane in my attic. So do I get every single signal? No, but I don't know what this, I think I did this yesterday. Right now I'm at 15,472 data packets that I've been able to download and decode. So this is a good way to just kind of get started beyond just listening to the satellites. That'll at least get you familiar with the software, with the satellites when they're coming over the horizon, those types of things. So let's say we actually want to work them. As I noted before, there are FM transponders, single channel, catcher effect, and those are the list of the ones that are currently up there. The analog transponders, CW sideband. If you've ever worked CW over a satellite, I don't know if any of you have done that, it's a real challenge because there's about 1.5 seconds delay between the signal going up and the signal coming back. So if you're trying to listen to your signal coming back to run the key, that DIT you send comes back when you open the key up. I can't do it. I mean, I tried, I just can't do it. So what I do is I turn the volume on the satellite down just enough so I know I'm getting in, and then I listen to the side tone, or even better, I use a keyer, and I just program it into the keyer because I know it'll come out right and I don't have to worry about it. Sideband works fairly well. You do have to adjust the dial frequency a little bit, but it's a great way to work it. There's examples, AO7, FO29, AO73, the XW series. Again, the point of the satellites is you have lots of targets for the effort. I've talked a little bit about the operational modes. The standard way of talking about it, you'll see, is the first letter is capitalized. That's the uplink, then a slash, and then the second letter, it's lowercase, and that's the downlink. So the three current modes that are out there are UV, 435 up, 144 down, VU, 144 up, 435 down, and if anybody has it, this is really kind of fun. There is an uplink on one of the satellites on, actually it's 1267 on L band. It's L band up and 2 meters down. They usually run that on AO92 on Sunday nights, and it's fun to do it that way as well. Any questions so far? Kind of okay? So let's say we want to work AO95, AO91, or AO92. You're going to need, well, let me start off with SO50 first. SO50 is a very old satellite. It was built by the Saudi government. Read, big satellite, high orbit, great parts. And it just keeps working along. It is 2 meters up and 70 centimeters down. The thing you have to contend with is Doppler shift. You know the old thing you learn about, or you notice when a train goes through, when the train approaches, the whistle gets higher in frequency. When it goes away, it gets lower in frequency. Well, exactly the same thing happens with radio frequency. It's a fixed percentage of the base frequency. On 2 meters, the Doppler shift is plus or minus 3 kilohertz. Now that's good news on 2 meters because plus or minus 3 kilohertz stays within the standard FM bandpass. So ideally you should be adjusting it, but if you don't, it really doesn't matter, it'll work okay. On 70 centimeters, on 435, the Doppler shift is plus or minus 10 kilohertz, which is outside of the standard bandpass. So generally what you need to load into your HT is 5 memory slots. 10 above, 5 above, the base frequency, 5 below, and 10 below. SO50 is easy to work because since it's 2 meters up and 70 centimeters down, you don't have to worry about your transmit frequency drifting outside of the bandpass. So you can leave your transmit frequency fixed and then just step through some memory channels on receive, which means you can do it half duplex. You don't have to be able to hear yourself at the same time you're transmitting. That really isn't the recommended way of doing it, but lots of people do. If you do it that way, be sure you're hearing somebody else before you start transmitting. Make sure that your receiving side is working okay. With AO 95, 91, and 92, you really need to be able to hear yourself, because there you can cheat and leave the receive frequency set, because it's always going to be within the bandpass, but you need to be able to hear yourself to make sure that your transmit frequency is staying within the bandpass and go through the steps. There are a number of ways to do that. This is kind of the extremes in HTs. This is a Baofeng, and they cost what? 35 bucks. This is a Kenwood D72. They're about a factor of 10 more expensive. This radio is full duplex, this radio isn't. The way a lot of people do it is they just use two Baofengs. One for the uplink, one for the downlink, one set on 2 meters, one set on 70 centimeters, and it works just fine. Another way of doing it, which is gaining increasing popularity and something the kids I think enjoy, is to use an SDR, a software-defined radio, a FunCube dongle, one of the RTL, cheap, you get them from China for, what, 10 bucks, the dongles, and they use that for the the downside. Capable of 2.5 kilohertz steps. Actually, you can get away with 5, but you do need the full duplex to be able to hear yourself. The antenna, whether for SO50 or AO 85 through 92, you are probably going to need an antenna. And behind you, if I can get at those without, I'll just kind of go through them in the order they are on the table, which may not be the way they are on the slide. The first one is an elk. This is a commercial antenna. It is a log periodic, so it is both 2 meters and 440 in one antenna. Before I go any farther, the other one is an Arrow, which I'm sure you've all heard about. People ask me which one I like better, and I usually try to answer that question by saying, which do you prefer, Fords or Chevys? Because it's that kind of an argument. The advantage of an elk is it's flat, so it's easy to throw in the trunk of a car. Because it's a log periodic, it only has one connection, which makes it difficult to use with two radios. But it's a perfectly good antenna. If you get an elk, the most common mistake from an elk that I made with my elk, everybody knows that when you're using an Arrow or any kind of a Yagi that the antenna attaches to the end of the antenna closest to you. So when I built mine the first time, I built it this way. And I couldn't figure out why I wasn't contacting to anybody. I was doing a wonderful job of irradiating myself, but I wasn't lighting up too many satellites. So if you decide to go the elk route, just be sure that the feed line is at the far end of the antenna and not the close end of the antenna. Also with the elk, well, let me talk to the other one and we'll quickly see the difference. The next antenna is the ever popular Arrow. So named because these actually are Arrow shafts. It is 3 elements on 2 meters and 7 elements on 70 centimeters. There are separate feed lines for each, so that if you are using 2 radios, it's relatively simple to hook up the 2 radios. If you are not, there is a 10-watt diplexer in the handle here. So you go from 2 radios to 1 for your handy-talkie. You will see people when they are using an Arrow twisting their hand. And what they are trying to do is align the elements with the apparent alignment of the antennas on the satellite in space. If you are using an arrow, one of the things you have to remember is if that's maximum receive, you need to do the arrow twist. You need to twist your hand 90 degrees when you go on transmit to put your transmit antenna in the same plane as the receive antenna. With an elk, you don't have to do that because it's all one. So both of these antennas are commercial antennas. They cost about in the $120 range for each of them. The last option, there are lots of options. The last option that my club built with, North Fulton, we've built about 20 of these so far. This is basically a home-built arrow antenna. The plans can be found on the web, VE2ZAZ. So this again is 3 elements on 2 and 1, 2, 3, 4, 5, 6 elements on 432. You need to twist it. The antenna itself was about $12. We built a jig for them. We used a combination of aluminum and brass. We used aluminum for the reflectors and the directors. We used brass for the driven element because you can solder to it. First, I tried to make them out of aluminum and see if I could make a satisfactory physical connection. No way. The expensive part of this antenna is actually in the handle. Again, it's the diplexer. It was about $21. There's a circuit board you can get from Far Circuits for it. And then it's got 3 surface mount capacitors and 3 surface mount inductors. So if you've never done surface mount before, this is a really kind of easy way to learn surface mount. Basically what it is a low pass filter on one side and a high pass filter on the other side to make sure the RF gets to the same place. But this antenna works. I actually put this one together and I used it with the Baofeng. One of the objections I get to working satellites is people say it's way too expensive. So this is a $35 antenna and a $39 radio. I'm now on the satellites. So this is the third option. If you want to look at these, I'll leave them up here. Be careful of this one because it's kind of an eye poker. I don't want anybody to get hurt. You're going to need a clock because, again, most passes last 10 minutes. Most FM passes last 10 minutes, and so you're going to need to know when it starts and when it stops. You're going to need a compass because these come over the horizon somewhere and they disappear over the horizon somewhere. Coming over the horizon is referred to as AOS, acquisition of signal. Going over the horizon is referred to as LOS, loss of signal. When I started doing it, we just did this up at Shelby, what was it, 2 weeks ago with Shelby? Is that right? I can't remember. I have road cones, little ones, that I've labeled AOS and LOS, and I set them out just to remind people. It's a very useful tool because if you don't hear something, you're going to go, well, I thought it was over here, but I don't hear it. So maybe I'm remembering wrong. Maybe it was actually over here. At least if you set a course for yourself and you said, this is AOS and this is LOS, you know it's somewhere within that cone that you've defined. A recording device is very, very useful. I use just a lot of people use their cell phones. This is just a little tiny cheap Philips dictating recorder that I got from Staples, I think. I put the little microphone by the earphone. The reason that is useful is particularly on the FM satellites, these sound like contest contacts. K7UDD, K4SQC, ABM74, QSL, please copy CN83, done. Well, that's hard to hear. And it's impossible to log. If you record it, 2 things will happen. You're going to get accurate logging, and the other thing I will tell you will happen, because everyone that's done this that I've been working with has found the same thing. You actually are making more context than you think you're making. When you start playing the recording back, it's like, oh yeah, I really did work that person. So those are the things that are useful. Any questions on this? Yes?
John, have you ever used one of the circular corkscrew antennas?
I use those primarily with my work with the International Space Station. There is a big argument that goes on as to whether circular polarization is better or cross-polarization. And cross-polarization would be the ability to switch between horizontal and vertical. Right. We do that all the time with an arrow just by twisting our hand. Some of the European stations have these, I'd love to see all their relays. They can go horizontal, vertical, right-hand circular, or left-hand circular on the same pass. And they've all come to the conclusion that cross-polarization is better than circular polarization.
I had built one years ago, again, back in Connecticut.
Yeah.
It was functional, but
yeah.
It was an exercise in exercise.
What he's talking about is with circular polarization, the way most of us achieve it on 2 meters or 430, 2 meters in particular, is you build one antenna vertically, another antenna horizontally, and either physically or electrically you separate them by a quarter wavelength. And what happens then is the way the signal comes out, it's like a corkscrew. It's a big circle. And like I said, big debate as to which is the best way to go on that. So, I've talked a little bit about Doppler for AO85 as an example. The FM satellites all have a PL on them. 67, don't forget to turn your PL on. I have a t-shirt that says, yes, I missed that pass because I forgot to turn my PL on. Why do we put the PL on it? Because taxi cabs think these are 2 meters is a great band for taxi cab radios, particularly in South America and Asia. We actually lost a contact on the International Space Station in the Philippines because there was so much taxi cab QRM on the 2 meter downlink frequency that they couldn't hear them. But there's an example of working through Doppler shift. So when the signal comes up, notice that the uplink is on 436.160. The downlink stays common. Most of us would simply load in 145.980. Then we go up 5. At maximum elevation, we're at the base frequency 436.170, then 175, and then 180. So that's an example of working Doppler shift through the contact. You're going to need some kind of pass prediction software. Well, which satellite is coming up, and where is it going to be, and when is it going to be there? Again, there are some sites out there. AMSAT.org is a great one for just plugging in your current grid, picking a satellite. SAT PC32, those are Linux, Mac, and Windows things that are available. There are a number of Android and iOS apps that are available. The one I like is called, where's the on-off button? It's called Android's, I'll pass this around. It's called AMSAT Droid. And what you get is a list for your current location of the next passes. In this case, it's AO85. And the other thing that's really interesting is if you want to work one, if you click on it, it'll show you where it's coming up over the horizon and where it's setting. The only difficulty I have with these, I keep thinking someone will be a billionaire when they invent a display screen for a phone that works in the sun. Because lots of times it's the middle of the day. So that's another way to, that's an important piece of things. I plugged in the grid for that, and this is actually what's going on as we speak. So what time is it now? 7:49. This is from SAT PC32. It was written by a German. So remember the format is day, month, year. I've tripped over that a number of times. Let's see, 7:49 or 8:49.
No, 23.
This is local time.
Okay.
I set it for local. So we're just about XW2A was only a 4-degree pass. When I do these, this is the really I think this is the really important column to keep up with. This tells you how high above the horizon the satellite is. This particular pass is 6 degrees above the horizon. Would I drop what I'm doing and went and grab my equipment to talk to that? Probably not. AO85, if I can find it, oh here it's in blue, at 9:01, ending at 9:15, it's a 14-minute pass, there's a 76-degree pass over us. So if you're here at 9 o'clock, or if you're home, you might want to set your radio to 145.980 and just see if you can hear anything it goes over. I'll bet you can with a 76-degree pass. That's virtually overhead and should be fairly easy to hear. But that's what PAX predictions look like for a number of satellites all worked out. Bhutan 1, Maya 1, and AMSAT, the reason those are all clustered together is those were 3 satellites that were built by the Japanese space agent. They were carried up to the ISS and they were thrown out as a group. So they're kind of all jumbled together. And all of them apparently are on the air. Past reminders, as I said, it's going to be visual, compass, visual reminders, elevation reminder, easy clock, tape recorder. Open your squelch all the way. These are really weak signals, and you just need to have your squelch open to be able to hear them. I didn't hear myself or anything. The most usual problems are, did you remember to set your location correctly? KEPS. KEPS stands for Keplerian elements, and those are, they're 2 lines of numbers that mathematically describe to the software where the satellite is in space. You really don't have to update those very often because none of the amateur satellites have propulsion on them, so they really don't change that much over time. The ISS is a totally different issue. The ISS is low enough that if they did not do what they call boost maneuvers fairly frequently, it would have re-entered and burned up a long time ago. Sometimes they also do maneuvers either up or down to avoid space junk. The ISS is traveling at 17,000 miles an hour. If something else is traveling at 17,000 miles an hour, that's a collision velocity of 34,000 miles an hour. That does a lot of damage, so they work really hard to get out of the way. What mode was it in? AO7, AO92. One Sunday I killed myself trying to work AO92. 432 up, 2 meters down. Oh yeah. Sunday is experiment day, and it was actually on L-band up and 2 meters down. So that kind of explains why I didn't make any contacts. I talked about the PL, and the last thing I would actually consider is rig and antenna issues. Do any of you operate, or have you operated 2-meter packet in the past? There is a packet repeater on the ISS, and it appears to be functioning again. Nobody quite knows why, but it is functioning again, as evidenced by these blue numbers here very recently of people who have actually made contacts through the 2-meter packet. The frequency is 145.825 up and down. It uses standard AX25 1200 baud unproto packets, and it's another way to make contacts. It's really kind of fun. The other thing, just as a heads up, the first week in October, I can't remember the exact day, is the 60th anniversary of the founding of NASA. NASA was founded in 1958. In celebration of that, there will be an SST event from the ISS the last part of September, the first part of October. They actually have a number of images that you'll be able to download as they fly over. Have any of you done SSTV lately? You have. Are any of you doing any of the digital modes? Because if you have the system to do that, you can do SSTV. The program we almost all use is called MMSSTV. You can Google it and find it. You can download it, and that will allow you to download these images that are going to be coming out of the ISS in celebration of the 60th anniversary of NASA. So that's kind of a... When you read the press release that will be coming from AMSAT, please be surprised when you see it. But that's another way to work with things. That's kind of what I had in terms of how you work the satellites. You must have some questions. What kind of things can I answer? Because most of you, I would imagine, own a handy-talkie or two. The antenna is buy it, build it. Some people do it with their standard Yagis. Bob Bruniga, the guy who wrote APRS, the APRS system, did some work for the Navy, and he showed that if you mount your Yagi at a fixed angle of 30 degrees above the horizon, you will receive 80% of the data from any of the satellites. Most passes occur between 60 and 0. A lot of them are less than 20 degrees elevation. So just fixing a Yagi at 30 degrees, you don't think you need an Azel rotor to be able to play in this game, because you don't. That 30 degree elevation will work great. Let's talk a little bit about amateur radio on the International Space Station. It's a program to allow students to talk with astronauts. We've done this over 1,000 times in the last 20 years. A contact lasts 10 minutes. It's a little different in terms of, think of it really not so much as a satellite contact, as a FM repeater contact with an odd split, because it's both 2 meters up and 2 meters down. We do it two ways. We do it direct. Direct is we take the antenna to the school. I've dragged my antenna system as far as Myrtle Beach to allow the school to do it. That was before I really knew where Myrtle Beach was, and I volunteered, and then I looked at the map. Probably not the best move, but the contact was great, and the kids loved it. Telebridge, there are 10 stations around the world that they will make the contact via amateur radio, and then over an 800 line, the kids will still be talking to the astronaut. This is actually supported, the Telebridge, by SCAN, the part of NASA that's responsible for communication, as another backup system. If everything else fails, this is another backup system to allow them to get information to and from the International Space Station. 10-minute pass, 250 miles up, 17,500 miles an hour. There are 2 project applications every year pertinent to what you're doing. That window is about to open for contacts for the second half of July 2019, July through December of 19. If any of you work with any schools, the kids think this is wonderful. They really do. I mean, if you've ever seen one of these, it's a really significant event. And what's interesting is their parents like it almost better than they do. But if any of you have any interest in this at all, get a hold of me. You can get a hold of me direct, or Bill knows how to get a hold of me. I'd love to see some applications from schools in this part of Georgia to do this. If equipment is going to be kind of an issue, you really do need an Azel rotor. As I said, we've got some down in Atlanta that we're happy to share and help supplement whatever you don't have. One of the things that's a little different about this is the crew can't do any Doppler correction. So we need to do it all for them, which means we adjust both the uplink and the downlink frequency. Recently, for years, we've been using the Ericsson. You'll hear that sometimes when people talk about it. That's basically a 5-watt handy-talkie. But 5 watts from 250 miles up works pretty well. There is a project to replace that Kenwood has generally donated 10 D710s that have been specifically modified for ARIS. It's going to return the APRS digital to full power. There's talk that we may actually turn on the voice repeater on the ISS. So that will be a really good one to hit. It will be co-located in the Columbus module, which is the American module with ham TV. We were aware that we had a ham TV capability up there. Yeah, we do have a ham TV capability up there on 2.4 gigahertz. It's really pretty cool. It's broken right now. But it's slated to come down. It's an Italian project. It's slated to come down, be fixed, and then it will fly again. It's DVB-S, so it's fairly easy to receive. The power supply is the issue. Believe it or not, the ISS has been up there so long, they've run out of plugs. There also is an issue that the US segment and the Russian segment are on different voltage standards. So we've had to come up with some new power supplies that will work on both voltage standards that provide extra plugs to give us power for the Kenwood radios. There is a project to do this. It's a $125,000 project. The big thing that's expensive is flight certification. You can't just go down to Radio Shack and buy a D700 and say, let's fly it. You got to prove that it's not going to cause a fire. One of the tests that we just finished passing was called RIP hazard. Are there any sharp edges on it that might tear a suit or cut somebody when they go by? Space parts are expensive. We have 10 radios. We need 10 units to be able to do that. And there is an opportunity to donate that if you want to see that happen. But this is, I think, a really fun way to involve your students in working with things. So, how are we for time? Do you want me to quickly run through the rest of what AMSAT's got coming up, or is RAM filled? Okay, so these are new satellites that are up there. I already mentioned them. Birds 2, those were thrown out on August 10th. Cirrusat, those were thrown out on August 15th. Those are all workable satellites with APRS and CW beacons. So those are fun to work with. There is a new mission called SSOA. It's being sponsored by Spaceflight with a Falcon 9 rocket. As I said, it's the first dedicated rideshare. It's got 70 spacecraft on it from 35 countries. 15 microsats, which is even smaller than a CubeSat, and 56 CubeSats. 56 of these. This is 1U. Some of them may be what they call 3U. You take 3 of these and you bolt them together. Some of them may be called what they call 6U. It's 3 by 2. Let's stick with the 1Us. Did I tell you about how these are launched? Yeah, spring. Yeah.
Watching the last downlink video they had of that, they're going to launch some CubeSats, thinking it was going to be something, no. He pulls them out of their launch tube, draws back like a baseball or a softball,
throws them.
Gives it a hurl.
The other way they get launched is something that's called a P-pod. A P-pod. A P-pod is a square tube that holds 3 of these. It has a door in the front to protect it during launch, and when they get to orbital station, they open the door, and there's a giant spring behind it. They give the command, the spring is released, and all 3 of these are pretty much the same way. They're just shot out into space. By convention, CubeSats can have no propellant on them, nothing that explodes. These rails, these are all beat up. These are called the launch rails. And those are very tightly machined because if you think about being in the P-pod, you don't want to be the first one in line closest to the door and you jam in the tracks. That probably wouldn't make you too popular with the folks that are behind you. Fox 1 Cliff will be a 1U cube. It'll be 432 up and 2 meters down. This will be another standard CubeSat that'll be an FM. So that's another one that's coming. Fox 1E, and this is the last of the Fox series. This one is going to be launched, I believe, by, at least last I knew, it was going to be launched by Virgin Atlantic. You know, they're going to try this one where you go up in an airplane, you drop the rocket off the bottom of a 747, and away you go. This will be 144 up, 432 down. This is going to be a linear transponder. So for those of you who like to work sideband in CW, this is another opportunity for sideband in CW. And that's the last of the Fox series. So what program is going to replace it? Project Golf, greater orbit, larger surface, higher is better. There's more coverage, easier tracking. It doesn't move as fast, but it's colder, which means you need more power because you're higher and it's colder. You need higher gain antennas, and as soon as you put higher gain antennas on, you need some way to aim the satellite so that the antennas are pointed towards Earth. There is more radiation to contend with, and the last thing is now you got to have some kind of propulsion on board because there is a federal regulation based upon an international agreement that says anything that's in orbit basically above a certain level, and we are above that level, you have to be able to deorbit it after 25 years. Space has turned into a junkyard, and you need some way when the satellite dies to get it back down. This footprint, this is a good example. The bottom footprint is at 520 kilometers, is the XF series or any of the AOs. You notice they're about the same. I don't know if you can see that very well, but that you could talk to anybody in that blue circle, which means if you're on a ship, you could talk to somebody on the coast of Africa. The circle on the top is AO7 at 1,400 kilometers. From the east coast of the United States, you can cover all of Europe. You can cover most of the western half of Africa. If this circle were over the middle of the United States, as I alluded to before, you could cover the entire United States. So the goal is to get back to that level in space. Golf T is the first one. It means technical exploration environment. It's going to be in the same orbit as everything else, but we're going to try some new things. We're going to try a linear transponder. We're going to try an X-band, that's a 10 gigahertz downlink converter, so that there will be 2 meters up and 10 gigahertz down. So for those of you who want to work with microwaves, that's a great way. There's going to be an ADC, an attitude. We're going to need to have deployable solar panels, ADT, attitude determination and curl, to point that 10 gigahertz antenna at the Earth. There is a power requirement. All of these now, if you'll notice, the solar panels are fixed on the side. In the one that's to come, they will actually fold out. We've never made folding solar panels before. So that's going to be kind of an experiment. Vanderbilt University radiation experiment, again, helps us get that free ride, or at least low-cost ride, and then a chance to find out if the software we've picked is radiation tolerant. You'll find very little, for those of you who are into computers, what's called VLSI, very large scale integration on a computer. That's where you pack just lots and lots of transistors on a single chip. The problem with that, if you've packed lots and lots of transistors on a single chip and you get one errant cosmic ray in the wrong place, you could be totally dysfunctional. So we tend to use smaller chips, not as tightly packed, just to make sure that we can survive the radiation environment. Golf 1 to go up and fourth quarter of 2020, that's the 1,300 kilometer order. That's up where A07 is. Again, this will be an all software-defined radio. For those of you who've worked with software-defined radios, the thing that's really, I think is really cool about software-defined radios, you write new software, you load it into the black box, and you just built a new radio. It's really quite an interesting concept. It's going to have it used to be called 5 and dime, a transponder on it that is 5 gigahertz up and 10 gigahertz down. The advantage of that is we get huge amounts of bandwidth for lots of CW, sideband, pictures. I mean, it's kind of like whatever you want to do. There'll be a camera on it from Virginia Tech, a great camera story. There is a camera on AO92 that was built by Virginia Tech, and they actually have some pretty cool pictures of the storm that they took with their amateur camera. They were delayed almost a year from AO91 to AO92 because at that time there was a regulation that said we need to make sure that you're not building a hunter-killer satellite that's out there taking pictures of other satellites. And so they had to go through this big falderot to make sure that the Earth was always in the picture, which they did. Only immediately post-launch to have somebody in the government say, that was really silly, let's cancel that regulation. So it was a lot of work for who knows what. And again, for this one, there will be that deorbit capability. This will probably be some sort of ion propulsion because again, same rules, nothing that explodes. AMSAT membership, I would be remiss if I didn't mention that. Basic membership is $44 a year. One of the things you get for that, and I'll pass this around, is an AMSAT frequency guide, which is a really helpful tool. It lists the uplink and downlink frequencies for all of the currently functioning satellite. It comes out once a year. It is particularly useful, I think, for the linear transponders, because at 20 kilohertz, at least when I do it, if I'm not careful, when I'm looking for a clear frequency, I can spin myself right out of the bandpass. The last thing I would pass around is a piece of nostalgia. When I started in satellites, there were no computers to do this. W3IWI wrote the first computer program to help with this. I ran mine on a Heathkit Z100. So absent that, we had to use something called an oscillator. And the oscillators were made for each satellite. The little circle here is my location. And what they would publish were equator crossings. And so you spin the dial to set the equator crossing, and then you can see whether or not the satellite will be useful. And there's 2 in here. I think this is AO7. And this, I think, was one of the Russian satellites. I can't remember. But that's the way we used to do it in the olden days. My first satellite radio was a Hamtronics. Anybody remember Hamtronics? Was a Hamtronics 10 meter to 432 transverter with a 10-watt amp on it, driven by an Argonaut 509. Which is a little digital radio with a dial on it. My downlink was an old Kenwood. It had a digital dial on it, and that's how I knew where I was, because I could set the frequency with the Kenwood multi-mode, and then as long as I could hear myself with the other one, I really didn't care how accurate the dial was. But nonetheless, that's kind of it. I hope to see you all on the FM satellites at least. If nothing else, set up that monitoring station. I appreciate your attention, and I hope I've answered your questions.